Welcome to ERC Tipsnology. This is part 3 of the field effect transistors tutorial. So the next topic that I will be discussing is about MOSFET or MOSFET. MOSFETs have characteristics similar to JFETs, and it has additional characteristics that makes them or make them very useful. There are two types of MOSFET, the depletion type MOSFET and the enhancement type MOSFET. By the way, MOSFET stands for metal oxide semiconductor field effect transistor. So the schematic symbol of the N-channel and P-channel depletion mode MOSFET are given below. So on the left side is the N-channel MOSFET or the N-channel depletion mode MOSFET, and on the right side is the P-channel depletion mode MOSFET. When we say N-channel depletion mode MOSFET, it has the arrowhead here pointing to the left inward. So it's pointing into the inside part of the MOSFET. And for the P-channel depletion mode MOSFET, you will notice that the arrowhead here is moving out or coming out from the inside part of the schematic symbol. So on the gate, you will see a line or a LED here. And on the right side, we have the drain at the top and the source at the bottom with a connection in the middle part of the arrow here. On the other hand, we have the same symbol here, the drain, the gate, and the source. Only the direction of the arrowhead is different, is pointing outward, and the N-channel is pointing inward. Now, the current and voltage designations and relationships are the same as for a JFET. The depletion mode MOSFET are very similar to JFETs except for one key difference. The depletion mode MOSFET can operate in two modes. It can operate in depletion mode, which operates almost exactly as a JFET, but it is defined by the VGS being less than or equal to 0 for the N-channel device, and the current flows through a physical channel in the device. For enhancement mode, it is defined by a VGS which is greater than 0 for an N-channel device, and the physical channel is enhanced by VGS to allow for increased or higher value of the ID or the drain current. Now, the output characteristics are here. For the N-channel depletion mode MOSFET, this is the typical characteristic or output characteristic. At the top of the graph is the ID, and at the bottom or the x-axis we have the VDS voltage. And this constant part here for the ID is also called the IDSS. And this is like the saturation point or the currents IDS for this are no longer increasing or decreasing. It will be constant. And from this point of VGS, positive 1.5 volts up to 0, or this is called enhancement mode, where the VGS is more than 0 or greater than 0. And here, when it is less than or equal to 0, this is called the depletion mode output characteristics. You will notice that the enhancement mode of the output characteristic is greater than 0, while those which are less than or equal to 0 volts for the VGS down to the value given here as negative 2 volts belongs to the depletion mode. So again, the depletion mode is where the VGS will be less than or equal to 0, and the enhancement mode is where the VGS is greater than 0. Now, in this case, the VP is equal, or the pinch off voltage is also called the VGS off. And the IDSS is equal to the, or the saturation point here is the ID when the VGS is equal to 0. And if you calculate for the VDS, it would be VGS minus VP. Now, as with JFETs, the MOSFETs have two regions of operation. We have what we call as the ohmic region, where the VGS is more than the VDS, or the VGS minus VP is more than the value of VDS. So when you calculate VGS minus VP, the answer will be less than VDS. Then this is the ohmic region. Same as the ohmic region that I have shown you before, where the ID is continuously increasing from 0 up to a certain value. As long as it is still increasing, that's called the ohmic operation region. Now, the saturation, or beyond the pinch off, or VDS, greater than VGS minus VP. So when the VGS minus VP is calculated, it will be greater than the VDS. So the saturation region of operation is where it will be beyond the pinch off. And the pinch off will be from this point going down here. That will be the voltage VP, or pinch off voltage. And from that point, the ID will be constant. Now, the ohmic region, as with JFETs, in the ohmic region of the MOSFET, it acts like a voltage variable resistor. Remember that a resistor can control the current, and varying it or changing it would mean that the current will also be varying. The higher the resistance, the lower the current. Because our JFET circuits can control the current by varying the voltage, in the similar way, the variable resistor is like controlling the current. So the variable voltage in the circuit that we discussed before is also controlling the current. That's why it's called voltage variable resistor, or VVR. And this is described by the ohmic region equation below. So you will see here the equation for the ohmic region equation. The ID is equal to 2 IDSS divided by VP to the second power, multiplied by VGS minus VP, multiplied to VDS, minus VDS to the second power, divided by 2. The source to drain resistance is called RSD, and this is approximately equal to delta VDS divided by delta ID, where delta refers to the difference between 2 points of the VDS, and the 2 points of ID will be the difference. The difference of the 2 points of ID will be called as the delta ID. Now, the saturation region in the N-channel depletion mode MOSFET, the saturation region is defined when the difference between VGS minus VP is more than the VDS. You will see here the transfer characteristic in the drawing here in the curve, and this one where it is intersecting the ID is called the IDSS, and from this point, this is called enhancement mode. And those lower than or 0 to negative, that will be the depletion mode here. And the transfer characteristic equation is equal to IDSS multiplied by 1 minus VGS over VP, or to the second power, or ID is equal to IDSS divided by VP to the second power multiplied by VGS minus VP to the second power. Now, as with the JFET, the behavior of the depletion mode MOSFET in the saturation region is modeled by the transfer characteristic as given in this graph, and by the transfer characteristics equation. So these are the two key specifications for the depletion mode MOSFETs. These are the IDSS here, and the VP, which is in the IDSS here, the VGS is equal to 0, and the VP here, where the ID is equal to 0. So this is the symbol for the enhancement mode MOSFETs or E-MOSFET. We have the uh, N-channel E-MOSFET here. You will notice that the line in the middle, the bar, is now cut into 3 pieces compared to the depletion mode MOSFET that we have discussed before. So in the depletion mode, we will go back to that. You will see that the bar here is a single bar. Whereas when we look at the symbol of the enhancement mode, the bar in the middle is divided into 3 parts or cut. But basically, they are the same symbol with the D MOSFET. Only the 3 bars here in the inside is different. This is called N-channel E MOSFET, and this is called P-channel E MOSFET. By the way, the arrow here is the same, going in for the N-channel and going out for the P-channel. So this is the schematic N-channel and P-channel enhancement mode MOSFET. So it lacks the physical channel of the depletion mode devices, so they can only operate in enhancement mode. And some minimum amount of VGS, there must be a value for VGS to be applied before a significant channel is created and significant drain currents can develop. And the minimum voltage is called the threshold voltage or VT. This is the minimum VGS needed to enhance a significant channel for ID greater than 0. So this is the output characteristic of the N-channel enhancement mode or MOSFET, or this is the normal output characteristic. So looking at it, we have here the VGS at positive 3.5 volts, and then positive 3 volts, positive 2.5, positive 2, up to positive 1.5 volts. And this is the VDS on the x-axis, and this is the ID on the y-axis. As with JFETs, the MOSFETs have 2 regions of operation. We have the ohmic region and the saturation region. Similarly, VGS minus VP is greater than the VDS, or the VDS is less than the difference of VGS minus VP. And the saturation or beyond pinch off is where the VGS minus VP is more than the VDS. So these are the equation for the ohmic region equation. This is the ID, which is equal to this formula. K multiplied to VGS minus VT multiplied to VDS minus VDS divided by 2 to the second power. And RSD is the source to drain resistance. RSD is approximately equal to the delta VDS divided by delta ID. So the third is the ohmic region, and as with just like JFETs or JFET, in the ohmic region, the MOSFET acts like a VVR or voltage variable resistor. Remember that the resistance controls the current and variable resistor controls the current. And because this circuit or MOSFET circuit can also control the current, it's called the voltage variable resistor, or it acts like a voltage variable resistor. And this is described in the ohmic region equation below. Note that this equation is different from the equations for other FETs. Now, the saturation region and channel enhancement mode MOSFET here, again, when you subtract VGS minus VT, that would be greater than the VDS. And the ID here is equal to K divided by 2, VGS minus VT to the second power. So the VT is along the x-axis on the VGS. When the VGS is equal to this point here, that's called the transfer characteristic, or this is the VT. So this VT has a value of ID equal to 0. That's the VT. And the ID will be equal to K over 2 divided by VGS minus Vt raised to the second power. So this is the saturation region defined by the difference of VGS minus Vt more than VDS. So just like the other FETs, the behavior of the E mode MOSFET in the saturation region is modeled by the characteristic or the transfer characteristic. So looking at this graph here below and by the transfer characteristic equation. Note that this equation is different from the equations for other FETs. Now, two key specifications for the enhancement mode MOSFET are K and VT, and IDSS and VP do not exist for E-MOSFET. It means that we don't have IDSS and we don't have VP for E-mode MOSFET. So in summary, let's look at this part 3. We have part 1, part 2, and part 3 of this FET or field effect transistor tutorial series. So we have the JFETs, are unipolar devices. JFETs have 3 terminals, the source, the gate, and drain. And the JFETs have a high input resistance since the gate source junction is reverse biased. And those capacitance that we do not want or unwanted capacitance associated with field effect transistors can be solved or resolved or dealt with by using dual gate type FETs. For IDSS, for all FETs, this is the maximum amount of current flow in the drain circuit when VGS is 0 volt. Again, the saturated IDS or IDSS or cut-off current for all FETs is the maximum current that can flow in the drain circuit, and that is the VGS must be equal to 0. Now, all FETs must be biased for proper operation. And we have the midpoint bias. This is the most common for use in amplifiers. Now, MOSFETs differ in construction in that the gate is insulated from the channel. Now, the D MOSFETs can operate in both depletion and enhancement modes. Although it's called only D MOSFETs, it can operate both in depletion and enhancement modes. But in E-MOSFET, it can only operate in enhancement mode. Again, the MOSFET can operate in depletion and enhancement mode, while E-MOSFET can only operate in enhancement mode. Now, for the E-MOSFETs, it has no physical channel, and a channel is just induced or produced with VGS greater than VGAS TH. Or it's like the Thevenin VGS. Now, E-MOSFETs have no IDSS parameter, and there are special MOSFET designs for high power applications. So there you go. This ends the tutorial series about field effect transistors. I hope that you, for those who like this video, to click like and share, and please subscribe to this channel towards our goal to help more people and towards our goal to reach 1,000 subscribers. Thank you so much. Bye-bye.